Okay, once again, I'm back. So today, finally some time to talk about math again. So today, what are we going to talk about? Huh? Today's topic that I'm going to talk about, okay, will be in regards to this famous French mathematician. His name is Francisco Viète. Okay, so Viète himself, he was a 16th century mathematician who specialized in developing polynomials and algebraic expressions and the relationships between their roots as well as their factors. Okay, but today that's not what we are going into. Today we are going to look at a very famous example that was discovered by Viète, and the topic will be Viète's quest for pi of infinite nested radicals. Now, this is the infinite radical that he actually discovered, nested radical. And today I'm going to show you how am I going to prove this relationship. So in 1593, okay, Viète actually discovered, okay, this entire identity. And it says that from the left-hand side, it says that the ratio between 2 and pi is equals to half of the respective nested radicals all the way to infinity. All right. So it's basically the root of 2 over 2, the root of 2 plus root of 2 over 2, and so on. The root of the root of 2 plus the root of 2 plus the root of 2 over 2, and so on and so forth. So Viète actually discovered this relationship. So today, the objective, I'm going to try my best, okay, to come up with a proof that can justify this with just using very basic elementary trigonometry, okay? So I believe everyone know that in high school, we learned the double angle relationship, okay, of sine, such as sine of 2x is 2 of sine x of cos of x. Okay, I believe everyone know this. And what's going to happen? I believe what Viète did was he actually expand this out. He actually expand this out, okay, by saying that, for example, you can see here sine, okay, will be equals to 2 cosine of x over 2 sine x over 2. Okay, because I can just half the angle, all right? And half of the angle is 2 times of the angle itself. Okay, so I hope you can see what I'm trying to establish here based on the identity. Okay, the two double angle identity. All right, so now what happened? Excuse me. Okay, so after that, what's going to happen is I keep 2 of cosine x over 2, I keep this. But for sine x over 2, I'm going to continue expand this out with the the double angle identity. So what's going to happen? Sine x over 2 can be expanded out as 2 cosine x over 4 sine x over 4. Okay, because it's half the angle one more time. Okay, so I'm going to go on further. So same thing, I keep this cos x over 2. Okay, cosine x over 4, I'm going to keep it this time. 2, I keep it. All right, and sine x over 4, I'm going to write it as 2 cosine x over 8 sine x over 8. Okay, based on the double angle identity. Okay, I hope you can see what am I trying to establish here. So this expansion, okay, this trigonometric identity is going to go on and on and on till an n term. Okay, so let's say we are going to move all the way to n term such that n is finite. For now, let's consider n as finite. What's going to happen? We can see that from here, 2 cosine x over 2, okay? And so on. Do you notice 4? 4 can be 2 square. 8 can be 2 to the power 3. Okay, the next one will be 16. Okay, will be 2 to the power of 4. So on and so forth with respect, okay, to x. And you can see that there is a series, okay, of cosine, okay, as it goes further and further, all right? So now what happened? So we can now at least establish that for n terms, such that n is a finite series, okay, we can get this relationship such that sine x, okay, is, okay, to the power of n with respect to all the cosine of half angles, okay, and so on and so forth. So it is actually the power of 2 gets lower and lower each time, okay, all the way to an n term, such that n is finite. All right, and definitely you end up with sine, the last term, the very, very last term will be sine x over 2 to the power of n. Okay, so I hope you can see the relationship. What am I trying to establish here? Okay, and of course, all the 2, when you multiply them together, you get 2 to the power of n, because let's consider there are n terms in this series. Okay, so what's going to happen next is I'm going to divide both sides of the equation with x. So if I divide by x over here, okay, I'm going to divide by x over there. All right, over here. So coming back, we are familiar with one of the limits, okay, in trigonometry, elementary trigonometry, and that is for the function sine x over x, okay, when x approaches 0, okay, the function sine x over x will approach 1. Okay, this can be further analyzed, okay, with the graph, okay, below. As you can see over here, if you're going to sketch a graph, all right, you can see that, okay, as the function approaches, the x approaches 0, the function approaches 1. All right, as you can see here. So this also signifies if I'm going to look at another function of sine x over 2 to the power of n over x over 2 to the power of n. Notice, excuse me again, okay, such that if x over 2 to the power of n approach 0, the entire function of sine x over 2 to the power of n will approach 1. Okay, I hope you can see what I mean. So in this case, what is going to happen? What are the criteria? The criteria will be such that n approaches infinity. Why do I say so? Well, because as you can see, for x over 2 to the power of n, if n approaches infinity, 2 to the power of n will approach infinity. So if the denominator approaches infinity, for any value, okay, of x, it will approach 0, because infinity is a very, very big number. For a fraction like that, it will be incredibly small, okay? That will give us approaches 0 in this case. So this is just, okay, a reference to the earlier limit, okay? But in this case, n has to approach infinity, okay, in order for the function to approach 1. Okay, so we have to keep in mind, okay, so we have to keep in mind what we have established here, because this is what we are going to establish later. So in the next step, if you look at what we have established earlier, remember the equation, sine x over x. So when we are looking at this, notice 2 to the power of n over x. If I'm going to look at the very last term, remember we are still in what we call a finite series. Okay, so at this point, it is still a finite series. All right. So the very last term, if I'm going to take this very last term and I'm going to throw it to the front, what happened? Okay, it will be 2 to the power n over x multiplied by sine x over 2 to the power n. So you see, if you look at this portion over here, this portion, do you remember it is the earlier limit that we have found, such that n approaches infinity. So in this case, if n approaches infinity, so if I'm going to re-establish and transform this entire series from a finite to an infinite series, okay, such that all these in-between terms will diverge towards infinity, such that n will diverge to infinity, this portion here will approach 1. So that does mean that here will become 1. Yeah, and we are going to only keep all the terms of cosines over here. Okay, but this time round, I need to put the triple dots at the back, because now n, everything here, every terms in this bracket here will now tend towards infinity. Okay, so at this point, from here to here, it will tend towards infinity. So Viète actually took an example such that x is pi over 2. Let's take pi over 2, for example, and we substitute them in. So if we substitute pi over 2 inside, okay, sine pi over 2, okay, over pi over 2, you get 2 over pi, all right, on the left-hand side. On the right-hand side, we are going to put this term in for x equals to pi over 2 into all these respective terms, all the way to infinity now. So in this case, you're going to substitute all this in. What is it going to give me? I'm going to get, excuse me, I'm going to get, okay, cosine. In this case, pi over 2 will be pi over 2 square. Pi over 2 square, in this case, is pi over 2 cube. Okay, and so on and so forth, right? So now, if you remember in high school, we have this identity, the half angle identity. All right, such a cosine of a half angle is the root of 1 plus cosine of x, okay, of the angle over root of 2. So if we're going to establish this, we're going to apply this, okay, this identity, okay, and you can see for every term in the infinite series, you can see that, for instance, cosine pi over 2 square will be equals to the root of 2 over 2. Okay, because we know we know that cosine pi over 2 square, okay, basically is 1 over square root of 2. So 1 over square root of 2, it can be established as the square root of 2 over 2. All right, I hope you can see what I mean. Okay, it's basically I just multiply both sides with the root of 2 over the root of 2. Okay, and that's how I get. Okay, so the next one, okay, we can apply what we have derived here for cosine pi over 2 to the power 3. Okay, we can substitute this in, okay, into the identity, and okay, out comes the root of 2 plus root of 2 over 2. Okay, oh sorry, the root of 2 plus root of 2 over 2. Okay, because very simple, we are just basically going to throw this in, because in this case, pi over 2 to the power 3 basically is pi over 2 to the power 2 over 2. Okay, I hope you can see. So this is a half angle of this, what we have derived. Okay, this is a half angle of this. So a half angle of this, okay, we just throw root of 2 over 2 inside. Okay, 1 plus root of 2 over 2 of the root, okay, over the root of 2 is this. So the same can be also applied for pi over x to the power 4. You can just use this. Basically, pi over 2 to the power 4 is half of pi over 2 to the power 3. So we can just throw this in. Okay, and we can derive the next nested radical. Okay, and in this case, you get the root of 2 plus the root of 2 plus the root of 2 over 2. Okay, so if you're going to continue this for 2 to the power 5 all the way to infinity, you will notice that you will form a very beautiful, elegant nested radicals. Okay, so that is what we have gotten. Okay, this will go on and on to infinity. So finally, for what we have just now, if we're going to substitute what we have from here all the way inside, what do we get? Simply, we will just get, okay, what we have derived earlier, and that is the Viète's nested radical for pi. Okay, that was what he have discovered in 1593. Okay, and I would say it's remarkable. One of the earlier discovery in mathematics for the estimation of pi. Okay, with series. So I would say that, yeah, this is pretty interesting. Yeah, and you can see that on the right hand side, all the radicals, okay, all the nested radicals form up in a beautiful manner. Okay, and yeah, this is something that is a great breakthrough in my opinion. Okay, and it's great. Okay, so that is how I actually prove, okay, Viète's formula, okay, using basic high school trigonometry. All right, so hope you enjoy. Thank you and have a nice evening ahead. Good night. Bye.